Okay, if you remember, yeah, I know it was a long time ago, but if you remember from our last lesson, we figured out a way to determine all of the possible rational roots for any given polynomial. So if we had a polynomial x to the fifth something something, it doesn't matter what happens on the inside, but let's say it ends with a plus 12. Now, does this polynomial have any real roots? Can we guarantee it has any real roots? It has at least one. Why? It's odd, x to the fifth. So the end behavior either looks like this and like this, or like that and like that. And we have no idea what happens in the middle. Well, that's actually a little too big. Yeah, that's like an x to the ninth. But anyway, so we know it has one real root. And hopefully I don't get my words mixed up today, because we're going to say real and rational. We're on 295. So today we're focusing on rational roots. So not real. All of the roots that hit the x-axis are real roots, and the roots that miss the x-axis are imaginary roots. We're focusing today on rational roots, which are nice roots, fraction roots. So if I had this x to the fifth, it could look like this, in which case it has one real and 4 imaginary roots. Or it could look like this, in which case it has 3 real and 2 imaginary roots. Or all of the roots could be real. We're not focusing on real, we're focusing on rational. And remember, rational numbers are fractions or decimals that terminate or repeat. Okay? And all of the rational roots, and this is a review from last time, the rational roots are positive and negative versions of factors of the constant. So the possible roots here are plus or minus 12, or plus or minus, and I'm going to go down, 6, plus or minus 4, plus or minus 3, plus or minus 2, and plus or minus 1. The idea behind that is, if you put 5 linear factors together, all of these factors start with x, because it's 1x to the fifth, and all of the constants will multiply together, all of those numbers will multiply together to be 12. So the only possible numbers that could go in there would be 12, 6, 4, 3, 2, and 1. Now, couldn't this be a fraction? It could be, but if that was a fraction, then this would end up not being 1. Okay? So the proof for the rational root theorem is more complicated than you might expect because of that fraction thing. But essentially, if you had x minus 1/4, that's the same thing as 4x minus 1. So you can convert any fraction here into a non-1 number there. So it's going to work every time. So this 12 was created by multiplying those 5 or 6, those 5 numbers together. So if you have a leading coefficient of 1, the constant will tell you the possible rational roots. Now, are any of those actually roots? We don't know. They might all be wrong, right? It is possible to build one that looks like this, and that number is negative pi. In which case, the only real root is negative pi, and none of those are right. So we're just looking at what are the possibilities for rational roots. They may or may not actually exist. Okay? So Let's look at another polynomial that has a leading coefficient. So let's say I had 6 x to the 4th, and then it doesn't matter what happens on the inside, and then minus, we'll say 15. So I know this can create rational roots, and the roots would be plus or minus 15, plus or minus 5, plus or minus 3, and plus or minus 1. But because there's a leading coefficient of 6, you could also have fractions. So we look at the factors of 6, 2, 3, and 6, and we divide each of those by 2 and 3 and 6. Okay? It is. So plus or minus 15 halves. Do I need to divide by 3? Because you divide it by 3 and you get 5, so we already have that. Plus or minus 15 over 6 simplifies to be 5 over 2. Okay. Now I move on to 5. Do I need to divide 5 by 2? Nope, I already have it. So 5/3 plus or minus 5/6. Then we move on to this. 3 over 2 plus or minus 3 over 2. 3 over 3 is 1. We already have that. 3 over 6 simplifies to be 1/2. And then we move on to the 1. 1 over 2 we already have. So plus or minus 1/3 and plus or minus 1/6. Now, hopefully by now you're looking at this and saying, why on earth would we do this? Well, once upon a time when I was in college, I heard a story about the method to factor cubic equations, x to the 3rd equations, and I've never actually seen it done. It must be really difficult because we don't do it. So nobody in their right mind is really going to write all of these out, except you guys did, right? You're not in your right minds, I guess. So all we're doing is teaching you what could happen. If you have an x to the 3rd or an x to the 4th or an x to the 5th, we're going to get really good at finding the roots without doing a lot of work. So you could look at this and you can say, all right, these are the possible roots. I might test some of these. I might test 1 to see if it works, or -1 and see if it works. And using this and other methods, you can narrow down the possibility of the roots for things larger than quadratics. Quadratics are easy to factor. So if we had an x to the 4th, and I knew one of the roots was 6, then I could use synthetic division to break this into an x to the 3rd, and that would eliminate most of these. Well, 6 is not actually an option. Let's say 3. So if I did 3, that would move this down to a 5, and that's going to eliminate over half of the possibilities. And now I'm down to an x to the 3rd equation. If I can find one more root, then I can factor it and get the last 2. So that's the goal here. We're teaching you the different tools that you can use to find the roots of polynomials that have a degree larger than 2. Okay? All right. So today, we are going to use, we're on 295, which is 19 to 51 odd. And it says, use Descartes' rule of signs to determine the possible number of positive zeros and negative real zeros. So, you guys know who Descartes is, right? Yes. So, mathematically, Descartes is famous for this. The xy axis is called the Cartesian plane. Descartes is the one who invented this. If only he would have had a graphing calculator, right? He's also an existentialist philosopher known for I think, therefore I am. Although I like the version I made up. I doubt, therefore, I might be. But nobody, nobody's ever published that for some reason. So Descartes said, if you look at the coefficients of a polynomial, where you have positives and negatives, if you look at the positives and negatives, that will give you a really good idea of how many positive and negative roots there are. So the rational root theorem says you look at the leading coefficient and the constant, and you can use that information to figure out all of the possible rational roots. And Descartes said, if you look at the signs of the entire polynomial, you can figure out roughly how many positive roots and how many negative roots there are. So let's go back. So if you look at 287, this is Descartes' rule of signs. So Descartes said, if the polynomial function p of x, so we have x to the n minus 1, all the way down, has real coefficients, and the first term is not 0, which if the first term is 0, then it's not there, right? So that's not a problem. The number of positive real zeros of the polynomial is either equal to the number of variations of sign of p of x, or less than the number by an even integer. So if you look at the polynomial and you put it in descending order, and you look at the signs, if you read from left to right, every time the sign changes, that means there's a possibility of a positive root. So if we had x to the fourth minus 5x to the third minus x squared plus x minus 6, you count what he called the sign changes. So did that sign change? 1. Did that sign change? No. Did that sign change? Yes. Did that sign change? So 3. 111. So he said, if you count the sign changes, that is the most the highest number of positive roots you could have. And then, oh, I bumped the book. Nice. And then there's an addendum to this, or less than that by an even integer. So as far as positives are concerned, there are 3, or less than that by an even integer. 1. You have to go down by 2s. Okay? And then the second half of this is equally easy. The number of negative real zeros of the polynomial is either equal to the number of variations of sign of p of negative x, or less than that by an even integer. Okay, so he said what you need to do is plug in negative x. If I plug in negative x here, is that going to change anything? Negative x to the fourth is equal to x to the fourth, right? So this would be positive. Would this change? Yes. So that would change to be positive. Let me switch colors. Would this change? No. That would stay negative. Would that change? Yes. So how many sign changes do you see? 1. So 1 negative root. So the negatives would be 1. So do we know exactly how many roots there are? There are 4 roots, so there have to be 3 positives and 1 negative. So when we go back to our other list of all of those plus or minuses, if we can find the negative one, then we know that all of the rest are positives. If you had to guess, we had that plus or minus 15, plus or minus 5, plus or minus 3, plus or minus 1. If you had to guess and use synthetic division to test, what sort of number are you going to pick? I would definitely pick a positive because there are far more of those. And then hopefully we could just find the negative by factoring later on. Okay? All right, so I'm going to work some of these with you. It might seem difficult, but it's actually really easy to do. Okay, so 19. So positives, negatives. How many sign changes are there in 19? So there's a sign change and there's a sign change. So the positive roots would be 2 or 0. Because you take the number of sign changes and then you subtract by 2 until you run out of roots. Okay? Now we have to go through and plug in negative x. When I plug in negative x, which signs does that actually change in the polynomial? The odd exponents. All of the even exponents will kill that negative through multiplication, and all the odd exponents will change. So it would be plus, minus, minus, plus, plus. How many sign changes are there? 2. So that 2 would match up with this. Oh, nope, never mind. Sorry. So 2 or 0. So what's the only way this is going to work? 2 positive and 2 negative. How come? How do I know there have to be positive roots? Well, there are either 2 positives or no positives. There are either 2 negatives or no negatives. How do I know there have to be 2 positives and 2 negatives? There are 4 roots total. So 0 plus 2 won't be enough. And 0 plus 0 won't be enough. So there have to be 2 positives and 2 negatives. Okay. Look at 21. Oh, it wants us to determine what they are. Sorry. Okay. So list the positive. Oh, I'm doing this wrong. Oh, yeah, I read 23. Okay, sorry. So hopefully that was good for you. So 19, I read the wrong instructions. List the possible rational zeros. What are the possible rationals for 19? Plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. So we need to test some of these. Which one would you start with? 1 is the easiest. So I'm going to put 1 in the box and do synthetic division. Am I missing any coefficients? No. So 1, 2, negative 9, negative 2, and 8. Drop the 1. 1 and 1 is 1. 2 and 1 is 3. It'd be 3. Negative 6. Negative 6. Negative 8, and 0. Well done. Okay? So the roots, I'm going to keep a root list up here, x equals 1. Now what would you try? You could try 2, you could try negative 2, you could try any of them. The lower numbers are certainly easier to test. So we'll put 2 in here. Drop the 1. 2 times 1 is 2. 6. So that would be 12. Negative 6. Did that work? 2 times negative 6 is not positive 8. So 2 didn't work. So you already have it written. You might as well change it to a negative 2 and see if that works. So 2, that would be negative. Now 3 minus 2 becomes 1. Negative 2 times 1 is -2. -6 and -2 makes -8. Is that going to work? No. So I now know that doesn't work. It's not 2. Well, it still could be 4. We don't know. Well, actually, good job, Jason. I see what you're saying. How do we know it's not 4? If I have 4 factors, if one of them is a 1 and one of them is a 2, then one of them would either have to be a 2 or a 4. I could have 2 times 2 times 2, and that would make 8. Or 2 times 4 would make 8. So it's got to be 8 or 1 again. Well, I would try 1. Well, it might work. It probably will work, actually. Because if 8 works, 1 has to work also. Okay, but it might be -1. Okay, 1 times 1 is 1. 3 times 1, or 3 plus 1 is 4. 4. That would be -2. That didn't work. So I'm going to switch to -1. So -1, -2, or +2. -1 times +2 is -2. That would be -8. That would be 8, and that would be 0. So -1 is another one. And now I'm left with x squared plus 2x minus 8. Does that factor? Wait a minute. I must have messed up somewhere. Oh. So I messed up. Okay. That makes sense, right? So you're going to test them until you get it down to an x squared equation, and then you can factor it. Okay. I should have put this on last time's assignment. That was my mistake. But whatever. Okay. So now, number 23. This is Descartes' rule of signs to determine the possible number of positive real zeros and negative real zeros. So for 23, how many sign changes are there? 1. Okay. And if I plug in -x, how many sign changes are there? So if I plug in -x, is that going to change? No. So we still have 1. So we know there is 1 positive root and 1 negative root. What about the other 2? Well, if we look at, well, let's do it this way. So flip back. What section are we on? 2.4. So if you look at number 23 in the answer set, it says +1 and -1. So what about the other 2 roots? Could they be duplicate roots? So is 32 a perfect cube, or a perfect 4th power? So if we have x to the fourth minus 32, that would be x squared that doesn't really work, does it? It would have to be 4 times 4, or... So, read this again. The number of positive real zeros of the polynomial is either equal to the number of variations or less than the number. This is the key right here. Real zeros. So there's one positive real zero, one negative real zero, and two imaginary roots. So if your numbers don't add up, then you end up having imaginary roots. Okay, 20, let's do 29. How many positive sign changes are there? So positive is going to be 1. Now we plug in negative x. Does the first sign change if we plug in negative x? So minus, the next one changes, the next one changes, the next one changes. How many negative sign changes are there? So negative would be 1. So there's one positive, one negative, and a whole bunch of imaginary roots. Okay. 31. How many positive sign changes are there? 2. So positive is going to be 2 or 0. And negative, that would remain unchanged, unchanged, unchanged. So we'd still have 2 or 0. So actually in this case, we could have 2 positive, 2 negative, and 2 imaginary. 0 positive, 0 negative, and 6 imaginary. 0 positive, 2 negative, and 4 imaginary. There are a lot of possibilities here. But if there's one positive, there's another positive. If there's one negative, there's another negative. Okay? And then we're going to 52, right? Yeah, they both decrease by an even number. Yep. All right, we're certainly not going to have enough time to finish this. Well, what I would do, I would go to 52 and just do the sign changes, and we'll do the combinations and the tests tomorrow. So don't hand this in. So go the tests. You're going to find all the roots. So on that last section, there are 3 parts. Determine the sign changes, and then list the possible rational roots, so the plus or minus 5, plus or minus 3, plus or minus 1. And then the last part is find all of the roots. So I don't care how you do it. Maybe you want to just do the whole problem, which might actually make more sense. So maybe you just want to go to 41 or something today. But we'll finish this tomorrow. The trouble with doing all of the part A's is you're going to run out of room, because you're going to be doing a lot of tests and sometimes they won't work. So maybe do to like 39 or 41 today, and then we'll finish this tomorrow. Okay? So on that last section, you have 3 parts. List the possible positives and negatives. List the possible rational roots, and then you're going to test them and find which roots they are. And by the way, graphing is not allowed, because you could graph this and find all the roots, right? Why don't we just do that? We're teaching you the tricks of the trade that you'll need later. So, okay, get to work.